Hey geometry geniuses, before we dive into angles of elevation and depression, wanted to show you this quick clip from the show Arrested Development. If you've seen it before, it's a great show. If you haven't seen it before, I think it's on Netflix. It's a good time. Let's take a look. And so there's this running joke with this scene about Charlie Brown. If you're not familiar, he is this cartoon. It's been around forever. That at some point in a few episodes ends up walking like this, looking down at the ground, being depressed or upset about whatever might have happened in his life. So for this section, we're going to kind of tie into this because we occasionally look down at the ground with our line of vision. And with trig, sorry to bounce back in, I know the videos are great. With trig, we use these angles of elevation or depression, whether we're looking up at the ground or down at the ground, to solve applications which may use these angles of elevation or depression that are created with our line of sight. So if we take a look at the examples here, we say that we have an angle of elevation if we're looking up at the sky towards our line of sight, and there's a horizon line that's created where we normally just look ahead, but now since we're looking up, the angle is created in here. So we call that an angle of elevation, which makes sense. Something's elevated up when we're looking at it. Where if we're looking at Charlie Brown's situation or the Arrested Development situation, we can call an angle of depression an angle that's created when we're looking down at something. So if we were on a cliff looking down at the water, we would say that we have an angle of depression because we're looking down in comparison to where we normally look straight ahead. So recall that with Charlie Brown, normally Charlie Brown would be looking straight ahead, but he's looking down at the ground. So think of that as a classic angle of depression. And so we tie in the trig situation seen here. We'll take a look at this one with a hot air balloon, a gentleman or person in the air balloon. We have this bird up here and we have this mountain. So describing these angles as they come about. So let's start with angle 1. So we could say that angle 1's up here. Well, we have this bird up here, and its horizon line goes straight to the air balloon, but it's looking down at the person. So what do you think about angle 1? Is that depression? Is that elevation? We would be saying that angle 1, since we're looking down, is an angle of depression. To the guy in the air balloon. For angle 2, what do you think about that? Well, since we're now at the air balloon rider's perspective, we are looking up, so we could say that if we were to follow this line up, we would hit the bird. So we would say this is an angle of elevation because the bird's higher up from the guy to the bird. For angle 3, this is from here to here. So this is the gentleman looking down at the base of the mountain. So we would say that's an angle of depression from the guy to the base of the mountain. And this is important because if we were just going to say, oh, it's the guy to the mountain, well, which part? Is it to the top? Or is it to the bottom? You'd want to say the bottom. Angle 4 is a little funny because it's taking a look at the very base of the mountain. And I guess since this is traveling upwards to the gentleman, so this would be an angle of elevation from base to the guy. Of course, the base of the mountain. That's what we're talking about. So being able to observe these is super important. We'll see some examples now with more trig. We'll take a look at example 2. So we have a site, a rock climber on a cliff at a 32-degree angle of elevation. Our eye level is 6 feet above the ground, and we are 1,000 feet from the base of the cliff. What is the approximate height of the rock climber from the ground? All right, well, recall that our eye level is 6 feet above the ground, which will be important soon. We know that we're 1,000 feet from the base of the cliff. We know it's an angle of elevation of 32 degrees. The approximate height of the climber from the ground. Well, I know the climber is way up here, and there's additional 6 here. Well, let's think. We have our opposite, which is unknown, and we have our base, and we know this is 32 degrees. So what trig function would use our opposite and our adjacent? What do you think? Should be saying tan. So we could say tangent of 32 is our opposite, which is what we're missing, over our adjacent, which is 1,000. And so we can take this a little bit further. So we know that if we were solving for this height, it would be 1,000 times tangent of 32. But we know we need to add on 6 if we're going to get that actual height from the ground. So let's add on 6 to that. And this would provide us our answer. So I always try to hold off on any calculator computation until I know that I got everything right, because I try to let the calculator take care of everything. So let's do 32 times tangent times g. We're adding on 6. So we can say that the approximate height of the climber from the ground is approximately 630.9 feet. Crucial thing here was adding on the 6 at the end. You don't want to throw that into the triangle. Let's see what else we got. We'll see some of these we have to actually sketch them out. Well, all of these look pretty solid. Let's see if we can find one with depression. The angle of depression of a buoy on the water from the top of the Barnegat Bay Lighthouse, 130 feet above the surface of the water, is 6 degrees. Find the distance from the base of the lighthouse to the buoy. Okay, so there's a lot going on here. So we have an angle of depression. So I'm definitely going to draw out my horizon line. I'm definitely going to draw a line going downwards from the top of Barnegat Bay Lighthouse. So let's draw this lighthouse as best as we can. That's what lighthouses look like nowadays, right? Down in Wildwood, New Jersey. Okay, well, we know that that's going to be 130 feet above the surface of the water. And it's 6 degrees, so top of the Barnegat Bay Lighthouse, 130 feet above the surface of the water is 6 degrees, so that's our angle of depression. Find the distance x from the base of the lighthouse to the buoy. And our buoy is out here. What do buoys look like again? They're like that. And they kind of round, they can float. All right, so we get this triangle. We know that this opposite is 130 degrees. We're being asked to find this distance x from the base to the lighthouse. We also don't know this. So tangent of 6 is going to be equal to our opposite, which is 130 over x. This is a little tricky how we can maneuver through this, but if we multiply both sides by 6, we get x tangent of 6. This equals 130. We can then divide both sides by tangent of 6. Cool, so x can cancel. I leave the calculator to do this work here, so have the calculator take care of that. You have 130. You're dividing it by 6, and then tangent This equals approximately 1,200. Oh, and I didn't want degrees on there. Sorry, 1,236 feet. Approximately. And that would be the height. Pretty cool. If you have any questions, please bring them to class. Thanks for watching.